In science, the term observer effect refers to changes that the act of observation will make on a phenomenon being observed. This is often the result of instruments that, by necessity, alter the state of what they measure in some manner. A commonplace example is checking the pressure in an automobile tire. This is difficult to do without letting out some of the air, thus changing the pressure. This effect can be observed in many domains of physics. The observer effect on a physical process can often be reduced to insignificance by using better instruments or observation techniques. Historically, the observer effect has been confused with the uncertainty principle. Particle physics. For an electron to become detectable, a photon must first interact with it, and this interaction will inevitably change the path of that electron. It is also possible for other, less direct means of measurement to affect the electron. Electronics. In electronics, ammeters and voltmeters are usually wired in series or parallel to the circuit, and so by their very presence affect the current or the voltage they are measuring by way of presenting an additional real or complex load to the circuit, thus changing the transfer function and behavior of the circuit itself. Even a more passive device such as a current clamp, which measures the wire current without coming into physical contact with the wire, affects the current through the circuit being measured because the inductance is mutual. Thermodynamics. In thermodynamics, a standard mercury in glass thermometer must absorb or give up some thermal energy to record a temperature, and therefore changes the temperature of the body which it is measuring. Quantum mechanics. The theoretical foundation of the concept of measurement in quantum mechanics is a contentious issue deeply connected to the many interpretations of quantum mechanics. A key topic is that of wave function collapse, for which some interpretations assert that measurement causes a discontinuous change into an eigenstate of the operator associated with the quantity that was measured. More explicitly, the superposition principle of quantum physics says that for a wave function psi, a measurement will give a state of the quantum system of one of the m possible eigenvalues Fn, n equals 1, 2, m, of the operator which is part of the eigenfunction psi n, n equals 1, 2, n. Once we have measured the system, we know its current state and this stops it from being in one of its other states. This means that the type of measurement that we do on the system affects the end state of the system. An experimentally studied situation related to this is the quantum Zeno effect, in which a quantum state would decay if left alone but does not decay because of its continuous observation. The dynamics of a quantum system under continuous observation is described by a quantum stochastic master equation known as the Belovkin equation. Further studies have shown that even observing the results after the experiment leads to collapsing the wave function and loading a back history as shown by delayed choice quantum eraser. In the ambit of the so-called hidden measurements interpretation of quantum mechanics, the observer effect can be understood as an instrument effect which results from the combination of the following two aspects: an invasiveness of the measurement process, intrinsically incorporated in its experimental protocol, the presence of a random mechanism through which a specific measurement interaction is, each time actualized, in a non-predictable way. A consequence of Bell's theorem is that measurement on one of two entangled particles can appear to have a non-local effect on the opposite particle. Additional problems related to decoherence arise when the observer too is modeled as a quantum system. The uncertainty principle has been frequently confused with the observer effect, evidently even by its originator, Werner Heisenberg. The uncertainty principle in its standard form actually describes how precisely we may measure the position and momentum of a particle at the same time. If we increase the precision in measuring one quantity, we are forced to lose precision in measuring the other. An alternative version of the uncertainty principle, more in the spirit of an observer effect, fully accounts for the disturbance the observer has on a system and the error incurred. Although this is not how the term uncertainty principle is most commonly used in practice,